In this laboratory exercise, we're going to do the Grignard reaction. The Grignard reaction is based on starting with an alkyl halide or some kind of halide. It's actually a very flexible reaction. Reacting it with magnesium metal. The magnesium inserts itself between the carbon-halogen bond. So you get this alkyl magnesium halide. This is the Grignard reagent. The Grignard reagent in the classic Grignard reaction reacts with a carbonyl compound like an aldehyde or a ketone. And the Grignard adds across that bond, and then we protonate it to make an alcohol. So in the classic Grignard reaction, you start with an alkyl halide and an aldehyde or a ketone, and using an intermediate magnesium carbon compound, you create an alcohol product. So the point of making organometallic compounds is we change the nature of our carbon. In most of the reagents we talk about, we have a carbon-based group bound to something more electronegative, right? So the halide then becomes the partially negative part, so the carbon becomes the partial positive. This tends to make the carbon the electrophile. But if we can change the nature of this bond, that is, if we can put a metal attached to the carbon, metals are less electronegative than carbon. And so in that situation, right, the carbon becomes the negative thing. The carbon can become the nucleophile. And so it gives us an opportunity that we don't have in other kinds of reactions to use a carbon as a nucleophile. And so here is the example in the classic Grignard reaction. Right? The carbon as the nucleophile can interact with a carbonyl because the carbon of the carbonyl is the thing that is negative and the oxygen of the carbonyl is the thing that is positive. And then the pi electrons can move to the oxygen to make room around this positive carbon, right? An electrophile either has space or can make space for a new pair of electrons. And we can create a new carbon-carbon bond as a result of that. Right? So our new carbon-carbon bond is right here. We make Grignard reagents by reacting an alkyl halide or a carbon-based halide with magnesium. And as I said before, the magnesium ends up inserting itself in the carbon-halogen bond. And so you end up then with the Grignard reagent or a carbon-based magnesium halide complex. This reaction is incredibly flexible. So it can work with alkyl halides of a variety of structures. It can work with situations where the halide is on a vinylic carbon, or it can work in situations where the halide is on an aromatic group. Right? So part of the value of this is that it was a very flexible reaction. We use an ether as our solvent. Right? The most common ether that we use is diethyl ether. although in some situations, tetrahydrofuran is used, right? The cyclic ether. Right? There are some other ethers that can be used if you need a higher boiling point or a higher reaction temperature. And so a higher boiling temperature ether during reflux would give you a higher reaction temperature. Here are a couple of examples. Here's a chlorocyclohexane, right? So this would be a secondary alkyl group reacting with magnesium at even cold temperatures. This would react quickly to form the cyclohexyl magnesium chloride Grignard reagent in 96% yield. Here is a bromobenzene, and you can see we get efficiency with different halides. It'll work with chlorides, bromides, and iodides. So here is our bromobenzene, an aromatic halide in diethyl ether at 35 degrees Celsius, which is about the boiling point of the ether. And here we end up with our phenyl magnesium bromide in about 95% efficiency. Here is a proposed mechanism for the formation of the Grignard reagent. In this proposal, the halogen, in this case the bromine with its unshared pair, interacts with the magnesium. That's going to then transfer some electron density to the magnesium, make it negatively charged. And so then the magnesium can act as a nucleophile. I know this is bad form. My arrow is touching my structure. Right? It can interact with that carbon, and then at the same time the bromine can act as a leaving group. And it's a better leaving group with the positive charge that it has right there. Right? So the interaction with the magnesium makes the bromine a better leaving group. And so the result is we have inserted our magnesium between the carbon and the halogen to which it was originally bound. And now, instead of that carbon being partially positively charged, now it's bound to something less electronegative than it, so now the carbon is negative. One of the things about this, the ether seems to stabilize this reaction. It does not go as well in other non-polar solvents. It seems that the magnesium likes to be interacting with four things. That is, it likes to be tetrahedrally coordinated. Right? Interacting with four things in a tetrahedral arrangement. And so the carbon-based group, the halide, form two of them, and then the oxygen from two molecules of the ether form the other two interactions to stabilize the transition state in the formation. One of the consequences of this making the carbon the negative thing in the bond is that Grignard reagents are very strong bases. And so if there's anything even remotely acidic around, they will take a hydrogen ion. And when they take that hydrogen ion, then we say that our Grignard is quenched, right? Because we just turn that back into a simple carbon-hydrogen bond, which we know is not polar and unreactive. And so the problem with that is it creates an unreactive product, which is not what we want to do usually. Okay? So that means anything that is protic, right, that can act as an acid in any way, that is, right, water, alcohols, amines, any of those things can react, and so we have to keep them away from the Grignard reagents if we want those Grignard reagents to act as nucleophiles in other reactions. The primary protic molecule that we're concerned about with a Grignard reagent is water, right? We know that there's water in the air and water contaminates lots of things. And so one of our challenges is, how do we exclude as much water as possible? Because if there's any water at all, the Grignard reagent will react with the water instead of the thing that we want it to react with. And then we end up with our non-productive product, right? Our non-reactive product. So that means we can't have any protic groups in the solvent, right? Remember, that includes water, alcohols, amines, or any other group like that. There can't be any groups in the halide, right? So the halide has to be dry, right? That is, it can't have absorbed water in it from the environment. So it needs to be fresh and dry, or you need to actively dry it by distilling it or by putting in a drying agent. But that also means in the halide, like if you have a chloride, there can't be an OH group in another part of the molecule, right? All of those would react with the Grignard faster than the halide, right? And in the thing you react the Grignard with, right? If you have your carbonyl, the thing we want to target with our Grignard, if there's something protic in another part of the molecule, that will react faster than the group we want, and so that would quench our Grignard, right? So there can't be any protic groups, water or anything else, in the reaction mixture. Do you get the feeling this is something I feel like I need to express, right? Our Grignard reagent can't be exposed to anything protic, a hydrogen bound to an oxygen, a hydrogen bound to a sulfur, a hydrogen bound to a nitrogen. So that means we can't have those things in our solvents, right? And we can't have them as other potentially interfering groups in the compounds we are using to generate our Grignard. So here's a quick example, using some information from this table that I found on the University of Massachusetts Chemistry Department site. It's their organic chemistry class. They had a good pKa table. And so we can see, right, the reaction we're using, we're going to make a benzyl Grignard, right? So this group is called the benzyl group, right? And so we can see here the benzyl group is the conjugate base of toluene, right? So this compound is toluene. So toluene is the acid, the benzyl group is the base. Well, we can see that the pKa for toluene as an acid is 41. And remember, the higher the pKa, the weaker the acid. And so if we're looking at water or an alcohol, right, those pKa's are in the range of 15 to 17, right? So, right, this is the stronger acid. Right? And toluene then is the weaker acid by a considerable amount. And so that makes the benzyl Grignard the stronger base, and the hydroxide ion that is produced the weaker base. And so the reaction will tend to go very strongly in that direction if given the opportunity. Whether this is water or whether we put an R group on there and that acid is an alcohol, that reaction will proceed and quench our Grignard. Okay, so once we've made our Grignard reagent, how do we use that to synthesize an alcohol? Well, as I said, we react it with a carbonyl compound, an aldehyde or a ketone. Right? And in that reaction, the pi bond of the aldehyde or ketone acts as nucleophile to interact with the magnesium as the electrophile. And in what appears to be a concerted reaction, we don't see any separate intermediates. At the same time then, the electrons from the carbon interacting with the magnesium move to the carbon of the carbonyl to create that bond. So essentially we get an addition across the carbonyl bond with the magnesium electrophile going to the oxygen and the carbon nucleophile going to the carbon. And so then we make our our alkoxy magnesium bromide intermediate. Now we don't worry about water, because now what we want to do is we want to replace that magnesium with a hydrogen ion. So we add aqueous acid to the mixture. The acid protonates the oxygen, frees the magnesium bromide, and then you end up with your alcohol product in 2 steps. Here's another look at the mechanism written out in sort of a standard ChemDraw format. This might help you put together your mechanism in your pre-lab. So we can see the chloride interacting with the magnesium, so magnesium is acting as the electrophile. But since that magnesium has its own unshared pair of electrons, those electrons interact with the carbon, but in order to make room for those electrons to bond, the chlorine has to leave. And so we end up then with our benzyl magnesium chloride product. Let me write that down for you. Benzyl magnesium chloride. Right? That is your Grignard reagent. Right? Then we will, after the Grignard reagent has been created, we will add our benzaldehyde as our electrophile. So the pi bonds interact with the magnesium, acting as the electrophile. Then that frees these electrons in the carbon-magnesium bond to go to the carbon, right? That creates that new bond, right? The oxygen-magnesium bond is new. And so this becomes our diphenyl ethoxy magnesium chloride intermediate. Once that reaction is done, we no longer have to be concerned about water because we're going to want to displace that magnesium anyway. So we will add aqueous acid. And we know that in aqueous acid, the hydronium ion becomes our strongest available acid in most cases, right, in an aqueous solution of a strong acid. So that alkoxide group acts as a base, right, to deprotonate our hydronium ion. We end up with our product, right, and in a solution of a magnesium bisulfate chloride salt, right? All this is soluble in the water. So now we can talk about the practicalities of what we're going to do in lab. Okay, so the glassware setup is going to look like this, and this is also in your lab procedure, right? So we're going to need 2 straight adapters to use as drying tubes. What we'll do is we will put in each of the straight adapters a little plug of glass wool in the bottom. Then we'll fill it with calcium chloride pellets. Then we'll put a plug of glass wool in the top to hold those in there. And we know that calcium chloride, and this is anhydrous calcium chloride, anhydrous calcium chloride will absorb water. So if any air is exchanged, if any air gets pulled into the apparatus, it's got to pass over the calcium chloride, and we hope it absorbs any water from the humidity in the air if there's an exchange, right? So like as we're draining our separatory funnel, air has to come in. We want to trap the water here before it gets into here. We will use a separatory funnel as an addition funnel, right? So that we can put things in here, put our drying tube on top, and add them without allowing too much extra water in. We will have a condenser. This is going to be a reflux condenser. So we want to condense all the vapors. So we will cool it with water, right? It is a reflux condenser. We will use the Claisen adapter, this Y adapter, so that we can have 2 things attached to our round bottom flask. Then we'll use a relatively large round bottom flask, pretty large for the volumes we're using. We're only going to be using about 50 to 90 milliliters, 50 to 75 milliliters, if I remember correctly. So it will be pretty shallow so that we have lots of surface for evaporation and for distillation. And again, the glassware will be in the oven because glass has a polar surface. Water tends to stick to the surface of glass. So all of this glassware will be in the oven. The Teflon stopcocks will have been removed. So you'll need to take them out of the oven when you come to lab. You'll need to use gloves because at this temperature, it can burn you. So you'll need to use gloves, set it up as quickly as possible so that not too much water gets inside. Reassemble the stopcock when the glassware is cool enough in order to be ready to do your exercise. The first lab may have to construct the drying tubes, but when that lab is done, those drying tubes can go back in the oven with the rest of the glassware. And so then they can be reused. The heat drives the water out of the calcium chloride over time. So we're going to start with 1.2 grams of our magnesium metal. Right? Again, we don't want to contaminate it with water, so do not touch it with your hands. Use gloves or a dry spatula. And that ends up being a little less than 0.05 moles. Magnesium has a coating of magnesium oxide on it, and that magnesium oxide coating will block the formation of the Grignard. And so we're going to gently grind that, just crush it a little bit in a mortar with a pestle to break up that coating before we add it to the round bottom flask. And then we will cover it with just about 10 milliliters of dry ether. Right? We'll use a total of 50 for the first step. And so you'll use about 10 milliliters. And then we will set it up and turn on the cooling water to get ready for our reflux. Then we will get 6.3 grams, about 5.7 milliliters, or about 0.05 moles, about 1 to 1. Right? I think these are within rounding errors of being close. One's a little more than 0.0495 and the other one's a little less, of our benzyl chloride. Right? We'll dissolve that in the remaining 40 milliliters of our ether. And we will put that in the addition funnel. Okay? When we've got that in the addition funnel, we will add about 10 milliliters of that solution to the round bottom flask, and then we will, right, one of my favorite things to draw, right? We will watch, right? We will take our little eyes and we will watch. And if a reaction is beginning, right, it will begin to reflux. Right? That is, the solution will begin to bubble a little bit and we will get condensation in our condenser. Right? The reaction also may start to turn cloudy and gray sometimes as the reaction begins. So look for those changes. If the reaction does not start in a few minutes, go back to your lab procedure for tips to help you get the reaction to initiate. Right? And this might include things like, adding a little heat. Right? Not on a hot plate, just with warm water. Right? In a beaker or a pan. Adding a crystal of iodine. Right? All of those things can help the reaction start if it's being slow. Right? If the reaction starts, or once the reaction starts, we're going to be confident here, then you'll start to add your benzyl chloride solution from the addition funnel, but you'll let it go in dropwise. And you just want to add it. The reaction is exothermic, so you want to add it so that you get a steady reflux. Right? My A looks too much like a D. Once you've added all the benzyl chloride. Then you're going to heat this under reflux for 15 minutes, right? So you will continue to reflux for 15 minutes to make sure that the formation of your Grignard reagent is complete. Now, while you are refluxing, right, once you've got all your benzyl chloride added and you're making your Grignard reagent, you can start to prepare your benzaldehyde solution. So you're going to take 4.2 grams, or right at 4 milliliters of benzaldehyde. And again, measure this in something that was in the oven that is dry. So you can take about 4 milliliters, or about 0.04 moles. So we've got a little less of this than we had of our other two reagents. What does that tell you about the limiting reagent? Right? And we're going to put that in 25 milliliters of our dry ether. Okay? So it's going to take a total of 75 milliliters of ether. Right? Once the reflux period has ended, then we're going to add that dropwise to the reaction flask, just like we did the benzyl chloride solution. We want this reaction to go slowly. We're going to add it dropwise. Periodically, we will stop to swirl the reaction to make sure it mixes. And then once it's all added, we will reflux that for 15 minutes. And then cool that whole thing in an ice bath, right? Cool our product mixture in an ice bath to get ready for the next step. While that is cooling, we will prepare our cold acid solution. So we will take 25 grams of ice and 25 milliliters of water and put them in a 125 milliliter Erlenmeyer flask. Now again, at this point we don't have to worry about keeping things dry, right? We've already reacted our Grignard. Then we will add 10 milliliter of concentrated sulfuric acid. Now remember, sulfuric acid is a strong acid, so a couple of points, right? First, we know we always add acid to water, right? That is a general lab rule, right? Because adding acid to water, mixing acid and water, creates an exothermic reaction, and you need lots of water to absorb the heat. Otherwise, you can get the water to boil and you can get a spattering of the acid, what you don't want. So you always add acid to water. And so once you have that solution made, you're going to slowly add that cold acid solution to the round bottom flask. That will then result in the protonation of our magnesium chloride, right? Our diphenylethoxy magnesium chloride is going to act as our base, right? It's going to take the hydrogen ion. And so then we end up with our final product in a two-phase ether aqueous system that then we will need to separate. So then we will transfer the contents of the round bottom flask, this ether aqueous two-phase mixture, to our separatory funnel. So we'll need to detach our separatory funnel and now use it as a separatory funnel instead of an addition funnel, right? And we should then get two phases, right? Since ether is less dense than water, our aqueous phase will be at the bottom. Our ether phase, which should have our product, will be at the top, or at least most of our product. So we will separate the aqueous layer, right? Put that in one Erlenmeyer flask. We will transfer the ether layer to a clean Erlenmeyer flask, right? So for this one, we can use the Erlenmeyer flask that we made our iced acid mixture, but we'll need another Erlenmeyer flask that is clean because the ether layer contains our product. We can take this aqueous layer. The aqueous layer will go back into the separatory funnel. We will add another 20 milliliters of diethyl ether. Right? Mix it appropriately, let it separate, and again, drain that aqueous layer. Right? It can go in, again, it can go in this same flask that we had the original ether layer in, because any product that was left in the aqueous layer, we hope now is in our second ether layer. Why do I keep doing that? Our second ether layer. And so we will combine that layer with the first one so that we can retain as much of our product as possible. At this stage, we will set up a simple distillation apparatus, right? We don't need a fractionating column. The boiling point of ether and hexane are enough different that a single theoretical plate in our distillation in a simple distillation apparatus is sufficient. You will probably want to cool whatever container you're catching the distillate, right? Put it in an ice bath, because if we're distilling away ether, it has a fairly low boiling point, and so we want to be able to keep it in our receiving flask. Okay, our receiving container. So ice, putting this in an ice bath will help. Okay. So we will transfer our ether layer, right? We're going to do our ether layer into a simple distillation apparatus. And then we are going to heat it and distill away most of the ether. And so as you're monitoring the temperature should stay in the range of 35 degrees Celsius as the ether is boiling off. When it looks like a good part of the volume has been removed, we're going to add 15 milliliters of hexane. And note, hexane has a much higher boiling point than the ether does. And so we're going to boil. And one of the things we remember from our distillation is that the temperature here is approximately the boiling point of whatever component is coming out. So this should be somewhere in the range of 35 degrees Celsius. As this starts to run out and this starts to distill across, one of two things will happen, right? Either the temperature will drop before rising sharply, right? Where we're going from 35 to 63. Or the temperature will simply, if there's enough heat in the system, go up. But again, we'll transition from 35 to, 69, right? That should have been 69, right? But the temperature will rise, right? So if you see that drop, that's telling you you're running out of whatever was boiling off at 35. If you see a sudden rise, that means the higher boiling thing is starting to come out. Either of those are indications that you have boiled away the remainder of the ether, and what you're starting to remove is the hexane. At that point, you want to stop your distillation and then transfer the contents of the round bottom flask to an Erlenmeyer flask and just allow it to cool. The product is less soluble in hexane than it is in ether, so we hope with sitting that our product will precipitate out of the hexane solution. Then you'll collect your solid product by vacuum filtration. After you've isolated your product, set your product aside to dry. You'll discard your distilled ether in the solvent container. Also, you will the hexane filtrate, right, should go down or should go in the solvent container. Your aqueous solutions we will collect, right? We will have a container for the aqueous solutions, those magnesium chloride salts. You'll need to wash and dry your glassware. If there are labs to follow you, return the glassware to the oven. But remember, before you put it in the oven, remove those plastic Teflon stopcocks. Okay? If you're the last lab, dry the glassware and return the glassware to the kits. Do not leave it on the lab bench. Set your product aside, come back in a day or two, right? Weigh your product to determine your yield, and then determine the melting point of the product. So I hope this is a good lab. It illustrates the primary reaction of the Grignard reagent, which is making an alcohol from an alkyl halide and an aldehyde or a ketone. Good luck.